What?
The video. I think first, just the video. First. Already pressed.
I've just done it.
Yeah.
It's blinking.
Thank you.
Okay. Now, this is a terrible and old picture. It contains all the physics of today. We have a plate with a free boundary and a free boundary, like this. Okay? Let's imagine that we don't have the other part of the plate. It's a plate. Free and free. All the energy will be reflected anytime. Okay? Okay. What we're going to write is a condition of interference between the multiply reflected waves. We can do it in two ways. First, geometrical. The answer is here. But actually, it's part of your last homework since next Monday. So we'll be very quick here because it's your homework. What is written there is a very simple and physical condition that is saying, by the way, this geometry here can be used for mechanical waves in physical plates and with the same formalism, but for a totally different physical system, for light waves in an optical fiber. The idea is all the same. Multiple reflections. There is no loss here. All the energy that is starting will be multiply reflected. Free, 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 free. Okay? Now, your homework will be, let me tell you just now, but I'm going to send it on Monday. What if this is rigid and rigid? Do you remember the string with open ends, free ends, and closed ends? Do you remember that the formulas were not changing except the eigenfunctions? Okay, that's your homework. So we did it. Now, the idea here is now, we have a plate with a given thickness. We're injecting a ray, so a wavefront here, that is bouncing up and down, like a ray. This is what we studied. Now, can we impose the condition that the multiply reflected waves can interfere each other? Geometrically, what we have to say is that the different, I have just two ends, so I cannot mimic properly, but all the wavefronts, the wave fields that are propagating there, they have to be in phase. Like progressive, regressive. Do you remember? Okay, it's the same. But we don't have a string. We have something more complicated. We have a plate. So we have more dimensions. We have angles. That's the only difference. So if you say that the difference in path between two different wavefronts is a multiple of a half a wavelength, then you're done. You remember the string? Okay, this was fixed and fixed. Let's consider it free and free. What we have to say is to accommodate something like that as a fundamental node, if you remember. And this corresponds that if the length is L, then lambdas have to be 2L over N, if you complete it. Now we made a period. You remember, I hope. The formula, the expression is the same also for rigid, rigid, closed, closed. What was different was the eigenfunction. Right? Sines instead of cosines. Then we derived right? And it's not changing also for close, close, rigid, rigid, or open, open. Right? You do remember this?
Yeah.
Okay. Now, this condition here is becoming this. what is funny is that this is your homework, but what we are going to do now is to follow the usual approach that we did also during the last lecture. It will be more algebraic, but we will see the fullness of boundary conditions. Okay. What we're going to write now is something that is propagating, in a plane due to the interference of these multiple reflected things traveling together along x with some velocity that is c. As we did for P and SP with one interface. Now we have two interfaces and the sage waves. So what we are going to write as a trial solution is something like that. Uy, it's an SH. Just one component of displacement. Something that is traveling along x. One section is going towards the negative, the other one is going towards the positive. It's the multiple reflection. So something going up, something going down. As usual, we are going to use the notation that we adopted during the last lecture. Here, we don't know the solution, if any, but kx becomes small k, omega over c, that is a horizontal apparent velocity, as we defined since 2 lectures ago. The part in zeta will be kz, will be described by r beta. Nothing is new here. We're simply writing something that is going up and something that is going down. We rewrite it in the usual way. Now, what are the boundary conditions? Well, it's a plate. Free and free. Right? Wake up. Okay. What is free surface? All the vertical components of the stress have to be 0 at the surfaces. Good. Now, since we are dealing with just Uy component of displacement, just one component of a stress should be considered. Sigma z y. Good. Let's write it. Mu times the derivative of the displacement. Easy. That's why I love waves. Because they are half of the algebra than gradients. One component of displacement, one component of stress. Now, where should we apply this condition? At 0 and for a plate 2h. Now you do understand that 2h is giving a physical dimension to the problem. Is it 1 centimeter? Is it 1 millimeter? Is it 10 meters? Is it 3,000 kilometers? Because that's our model. We will see later why. Okay, let's apply it. You write it, r beta, where in z equals 0 and in z equal to h. They have to be 0. It's the boundary condition. You do understand, without this one, we will have just a reflection. One is going up, one is going down. Game is over. We did it. It's going to give Snell's law. And the amplitude of a reflected wave will be exactly the incoming one. So 1, 1. But now we have another boundary condition that is telling everything that is going down has to go up, down, up. Okay? It's here. Now, if you apply these two boundary conditions with this solution, what you're going to get is is exactly the same expression that was written on the first slide that we have seen today. That is supposed to be your homework. And what we're going to have is that. Wait a second. you remember something that is similar to this one? Simpler, but similar? Well, actually, it was the string. When you write this one was coming from the fact that if you consider, for example, an open like this one, and you use the cosines, n pi kl should be n pi. Closed, okay, it's the same, but it's the sign. So actually, we found KL is equal to n pi, and this was giving this. That was valid in one dimension. Now, where do we have a string? Actually, we have a string. It's here. It's in the here. Now, let's imagine, for example, that we have a ray or a wavefront that is exactly going in this direction. Normal incidence, right? It's going down, going up, going down, okay? What about R beta in that case? Because the only difference between those two expressions is that we have R beta on the left, on your left.
And it is 0?
Equals to 1.
What is R beta? If you remember, I told you when we defined it, actually it's containing the angle. Now, according to the reference system that you adopt here, actually there, in that case, the angle is 0. So everything is in kz. You remember what was happening when everything was kz in the good old slide that I told you? I was going to show it at least one other time. What is it? It would be here. So let me open it. Okay. You remember? And I told you, let's imagine that we are sensors and we are measuring horizontal apparent velocity. We take clocks and we measure the time necessary for information to travel from me to you. If we are bouncing together, time is 0. Horizontal apparent velocity is infinite. And we're bouncing together. Okay. On the other side, if the angle is, in this case, not 0 but 90, what we would measure was exactly the wave speed. Let's imagine now we're not bouncing together, but the wave is arriving like that. Then we thought, okay, all the intermediate situations was c going from infinite to velocity. Later in the course, also during the last lecture, we found that when velocity is less than the wave, we have an exponential, imaginary exponential. I hope you do remember. You remember the definition of R's? So from infinite to velocity, in that case it's 0, to something that was less than 0, so imaginary, so damping. And we have used along Z. Okay, let's remember this. What I'm going to tell you is that situation, or the string situation, is exactly like the string problem. And actually, if we imagine normal incidence here with 0 angle, what we feel about the plate is just its thickness. And it's like a string. We're feeling 2h. 2h instead of L. N pi. N pi. R beta is telling us the angles. Okay. Now, let's imagine. 0 angle, 90. Now the wave will travel along the plate, satisfying the boundary conditions, and it's going to travel like an SH wave. Okay. Now, what is this? Are you on strike? For today it's fine, but look, this condition here was given this one. And then frequency, modes, velocities, and actually, in this system here, if we take omega and k, omega is here. If you multiply by 2 pi, 2, like that, omega and k, here it was a straight line whose slope was v. Right? That's the string. No dispersion. But please give a look here. Now our beta is containing velocities. C. Because remember that now is this. Now beta is not containing dispersion because beta, sorry, it's not the same mu. Beta has no frequency. But what about C? Because now we are looking for the C's. We're looking for the eigenvalues solutions of our problem. And if you put the expression of our beta here, and if you're going to look for the omega and k relation, what you get is this. You can deduce it immediately. If you write our beta out. Now, what is this? Wait a second. When n is equal to 0, that is fine. N equal to 0 means omega and k are related linearly by beta. Nice. And that's beta. What if n is equal to 1? It's a solution. Like here, n could be 0, 1, 2, 3, 4, forever. But all the modes of a string here, we're following the same line. Here it is not. When n is equal to 1, the curve is a little bit different. Something like that. When n is equal to 2, n equal to 3, and we have just 1 hour and a half, so I cannot plot all of them. Try to put n equal to 1 and to write the curve between omega and k, it will be an hyperbola, whose asymptote is always this. Now, except for n equals 0, n equal 1, 2, 3, 4, they are not lines. They are tending to be a line. When omega is very large and k is very large. What is k large? K is 2 pi over lambda, when lambda is very small and frequency is very high. Actually, they are so small, they don't feel the thickness. But if you make the plot of this, it is something like that. Now, actually, this is a totally different example of dispersion, because when omega and k are not related by a simple line, we have dispersion. And accept n equals 0, when n is equal 1, 2, 3, 4, omega over k and d omega over dk, they are different. Look here, for example. The omega over dk is starting from 0. Then it's getting larger, larger, larger. And then this will become similar here. No dispersion. Now you should remember your first homework, the forbidden zone, or something like that. Because the first mode cannot propagate here. What's happening there? First homework. We have damping along x. Kx is imaginary before that frequency. It's trapped. Then, when omega is higher than this, okay, go. The same for this, at higher frequencies. Now, what do we have here? The simplest and beautiful example of modal dispersion. Because we have a dispersion that is not caused by intrinsic dispersion. Velocities are not dispersed. Beta is not frequency dependent. It's not due to discreteness. We don't have lattices here. It's not caused by nonlinear terms. It's caused by interference between multiply reflected waves. Now, what is fun is that this picture is coming also from optics and optical fibers. So if you take light waves, insert an optical fiber, you get the same picture. Now, that's a way to give a look to this problem. There is another plot that is maybe more intuitive. It's about C. C is what we are looking for. What are the solutions of this problem? When we have dealt with radio waves during the last lecture, C was just a number, just one. 92% of beta. Do you remember? And we had only one condition, P and SB, going together. Now we have two. And we are imposing the condition of interference between up and down. So interference between multiple reflections. The message to take home is radio waves are due to the interference, also at the one interface. The bad news is that they can interfere also here, between P and SB. What about SH? Well, with one, nothing. But with two, okay, multiple, so interference by multiple reflections. We apply the boundary conditions, and we get this. What we're looking for, what are the eigenvalues? Well, those are the eigenvalues. And you can plot them. And from today on, when you're speaking about this kind of modes, C, that is horizontal apparent velocity, actually is called phase velocity. Why? Because we have dispersion. So we have to speak about phase velocity and groove velocity. They are different. Now let's give a look to phase velocity. Those are the solutions you see. You do understand that here there is no rocket science. It's just a geometrical condition. Beta is given. Once you give mu and rho of that plate, it's over. It's homogeneous, it has a thickness, and it is here. It's the geometrical condition of interference. Now, what if n is equal to 1? Look, straight line. This is normalized to beta if you want. So the fundamental mode, and we're going to call it the fundamental mode, like this one, or like this one, with rigid and rigid, that has no zeros inside the plate along Z, is not dispersed. The only possibility for a perturbation To travel like that is to go straight. And it will travel like an SH wave. Sorry, it's going to make something like that. UY, UY. Okay? It's going to travel with the same velocity, that is beta velocity. But when you had the possibility to be zero, and so on, well, the situation is different. Look at this one. It's starting at a given frequency. It's starting with an infinite. Because if you go to the cutoff frequency, these are called cutoff frequencies like in your first homework, C will become infinite. You could say infinite velocity. It's a horizontal apparent velocity, do you remember? We are bouncing together. What does it mean? Condition of interference is saying, okay, you can go up and down like that. And something is going to travel along X with infinite apparent velocity. Everything is bouncing up and down, taking this with a zero inside. I don't have enough ends, that's why in 1 second the displacement will appear. What about the perturbation that is carried? Once we have the set of C's, what we can do is to go back in the expression of the displacement, and to plot them. Eigenfunctions. The eigenfunctions in the string were very simple. Cosines, if free, or sines, if rigid. Okay? Let's give a look to the displacement here. Look, I'm sorry, because I've not found a better plot than this one. I found very nice animations that are later, but they are coming from EM waves. But the meaning is the same. Now let's give a look to this. This is called fundamental mode. The arrows you have to imagine that are dealing with displacement along Y. Okay? So you see the arrows are all going in this way or in this way. In this way, there are no zeros here. And keeping the boundary condition satisfied, something that has no zero in the middle of the plate has to go like that. So it's an SH wave going like that. And they have to travel like that. If you're adding a zero, now you have something that has a zero in the middle of the plate, part of it will go towards you, part of me will come towards me. Something like that, okay? Out of phase. Why? It's like a string. It's a free surface. So on the top, it has to be maximum, okay? With 1 0. But this condition of interference is not valid for all the frequencies. Here, they are damped. They cannot propagate. They're stopping. Then they are starting with infinite horizontal apparent velocity. What does it mean? It's something that is coming up and down, up and down, up and down. With higher frequency, what's going to happen? The angle is changing. The thickness of the plate is seen differently. You can imagine that when you are bouncing up and down, the thickness that you are feeling, let's imagine to be a ray. Up, down, up, down. In that way, what you feel is 2h. Now let's imagine a ray that is tilted a little bit. Now, you're going to feel this longer. It's going to be thicker. It's not. But you feel it thicker. So your interference will happen later. So from this angle here, now you're going to go to 90, and now you're traveling practically like an SH wave in this direction, like that. For the next mode, I don't have enough ends. Why? Because it's like that. Now it has two zeros. One is coming to you, one is coming to me, one is coming to you, one is coming to me, and so on. Like a string. What I'm telling you is that if you take the profile, the vertical profile, it's like a string with three ends. But now we have an additional feeling of it, because according to the variable, we can feel that string longer and longer. And when you're like that string is infinite. I know it's messy. It's not easy to imagine. You can say it's pure mathematics. That's why in your homework of Monday, I'm going to ask you, write the geometrical condition of interference, okay? Up and down, then they have to be out of phase with an integer number of half wavelengths, like that. And I'm going to ask you, what if the plate is not free and free, but rigid and rigid? 1 minute. Nothing is going to change. Not in the formula upstairs, not in the plot. What's going to change is this. Because instead of showing cosines, you will have sines, because it has to be 0 and 0. What if I'm going to tell you, look, one part of the plate is free, the other is rigid? You have to remember the string, and in 1 minute you can answer. Now, the rigid boundary condition is not important for the Earth, but it's important for acoustics, because you can imagine a tube, or better, a space with air limited by something that is rigid, and you're going to speak inside. And you can speak at a very long distance, like whales are doing. And it's called the SOFAR channel. That will be your third question. It's nothing else than the condition of of interference between multiply reflected waves. If you put there sound waves, it is the same, they will be longitudinal. The boundary condition will be rigid and rigid, but it will be the same. To carry energy away from a source, like an optical fiber, like an acoustic duct, like a plate like this with free. Now, question to you. Why we are studying this system here? If we want to deal with the Earth. Is the Earth a plate? Well, no. But if you do remember, the core mental boundary is a boundary between a solid and a fluid. Right? So actually for S waves, it's not homogeneous, but for S waves, it's like a plate. Now let's imagine to take, you remember the last animation of the last lecture? There was a hole inside. Now if you take that sphere, you imagine to drill it and to open it, it's becoming a plate. On Monday, I hope, you will see again this picture, but for the torsional modes of the Earth in a totally different geometry and for a much more complicated model. It will be practically the same. Question to you. What about PSV waves? Is the Earth a plate? No, because in the fluid part, P can exist. So it's not a plate. That's why we're not going to solve this problem for PSV waves. You know why? Because I'm lazy. Because you could do that. And what you have to do is to double everything. You have to write two components of displacement, ux and uz. You have to write two components of stress, sigma zz and sigma zx. You have to apply twice the boundary conditions. And what would you get? Lamb waves. They are so nice. Well, they seem like worms, but But I'm lazy. And we're not going to do the algebra for this problem. And I'm lazy, but not totally crazy. We're not going to do this one because it's not useful for the Earth. Because we don't have a free. We have a free and something is going down, the P waves. But for SH, the plate is a very good model. The simplest good model that we can imagine. That's why Session and Sadia used the modes of a plate, of a spherical plate, to produce the beautiful animations that we have seen at the end of the last lecture. So they used a more complicated version of these ones. Now, to conclude this part, let me show to you some animations for these waves. But we have two problems. Well, you have one, me. I was not able to find the animations for this problem. Nowadays, we are going to use SH waves in plates in labs with microchips. So the plates that are going to be studied there are microchips. It's not the Earth. But there is something similar. I fear that the link here is no more working. Because some time ago it was not working. Oh, well, part of your, it was a researcher dealing with optical fibers. Department of Electrical Engineering. What are we doing here? That's why I was grabbing these ones. Now, these are animations for EM waveguides, optical fibers. They are a very good process of visualization. They do not totally fit, but okay. Let's give a look to the top of a plot of these animations. What's going to happen there? You see that blue and red try to exist in that tube that actually it's an optical fiber, but you see that it's not able to propagate. It's damped. The first animation corresponds to a mode of an optical fiber that is beyond the critical frequency. Here. So you can plug in that frequency, but it's not going to damp. It's not going to propagate. E2 minus E2 ikx is becoming something E2 minus k star x. Yk, k is omega over c, please remember. It's not velocity, it's this one. So it's damped. Like your first homework. Then it starts, and you see the second animation. Now everything is coming blue and red, and if you sit on the top of the optical fiber, we will move together. It's an optical fiber, but let's imagine to be a mechanical analog. And you see that on the top, if we sit on the top, we're going to move together. It's infinite. Now, do you remember when I was asking you, what about the power of transmission of energy? Because in this point here, phase velocity is infinite, but this is zero. Zero group velocity means that actually energy is not moving laterally, it's standing. What's going to happen next? Okay, now we're going towards this part. Well, omega over k is this velocity, and group velocity is less, but it's not zero. Now, let's give a look to this. Now, that's a progressive way. But standing, this is progressive. And now it's moving, with no zeros. That's why it's not perfect analogous here. But you see that here we can measure horizontal apparent velocity. And also here, but it is lower. And here we have a 0. Now, these animations are giving an idea of what we want to study. But luckily, 1 year ago, or 1 year, something, Dr. Russell was helping me. Not me, but us. And I have a better analogous, and it will be a helper for your last homework. Actually, the solution of your homework is practically here. But I have to open. You can make an experiment, please. Remember, well, the Russell website, you know it very well. We have used it for the animation since the first lecture. If you look for waveguides, you will see this one. Now, this is using Mathematica Player. And on the browser, I cannot open it. Maybe it's my problem. So what I did was something a little bit obscure, but I downloaded, let's see, should be somewhere. Where is it? Oh God, maybe I lost it. Okay, it's going to take a little bit of, oh, maybe I don't have Mathematica Player here. Oh my God. It should be this one. Okay. Okay. That's the best analogous that we can imagine for SH waves in a plane. It will not be SH waves in a plane. It will be acoustic waves in a duct. Rigid condition and, let's say, P waves. I hope it's going to work. It's not working, but it's working. Okay. Let's try to make a recap here of what we're doing. That's only an animation. We started a long time ago with this. Come on. Okay. Progressive waves in an infinite medium. Sound waves, P waves, and stuff like that. Are we okay with this animation? Is it a yes?
Yes.
Yes.
Then we considered boundary conditions. And I have to find it. Standing. Here it is. We discovered modes. You look at the string here. Plots, remember. And this. It was a boundary condition. In a 1D system. Do we agree on this? Progressive, interference, standing. Okay. Now we can deal with a much more complicated thing. Because now we don't see, but actually it's a rigid, and the modes of an acoustic waveguide. It's your last one. Look, here we can play with frequency and with modes. Now let's imagine that you are standing on the top of this waveguide and you're listening. What you're going to get is something very similar to the first animation. It's a progressive wave, and we're going to listen sound here, and you see nothing is happening inside. Now let's take the first mode. Okay. Now, if we stay here, we don't hear anything. It's damped. Because in this animation, all of the higher modes have a cutoff frequency that is decided exactly at its, so the first fundamental mode has a cutoff frequency of 1. If I stay below, you see it's not moving. Now it's moving a little bit more, but still standing, damped. Now let's try one. Oh, now we are at the cutoff. Now let's imagine to stand on the duct. Now we all listen to the same sound together, because on the top it's moving in the same fashion. Infinite horizontal apparent velocity. What about the transverse, the lateral flux? Nothing, it's standing. Zero group velocity. Here in the middle, silence. Now let's increase. Uh-oh. Now still a zero here, but on the top, now we are listening to something that is moving with some velocity. We can increase it. And from infinite, the phase velocity, now you have to count the velocity of this maximum minima. It's getting slower actually. Here it was infinite. It takes no time. We are bouncing together. Remember, these are sound waves. For SH, you have to imagine a different displacement, but it's the same. Okay, look, this is coming slower and it's going back to sound velocity. Now let's do it for 2 or 3, not anymore. If now we go to 3 with this one, not bad. But here amplitude is much lower. If we go to 2, damped. If we go to 4, now it's not easy to, that's the third mode, that's why I was, okay. Now look on the top, all the points are moving together. So, okay, my friends, actually this is the answer to, most of the answer to your last homework. That is going to be sent on Monday. You know why? Because still we're missing one part. You have to know that whales are talking in some way in the oceans using an acoustic waveguide. Now, do you know if there are any rigid interfaces in the ocean? Inside the ocean, not on the bottom of the ocean. You should say, no, there is nothing rigid there. But there is something that is called a low velocity channel. It's not low velocity channel, it's going to be called SOFAR channel. And it is marked by an inversion of velocity. So it's not a very perfect waveguide, but it has a low velocity layer. Okay, to deal with the last part of our surface waves, we should define more accurately love waves. SH waves in the plates are like love waves. But the system that we have to consider is not exactly this. It's this. And this will be our last but not easy topic for today. Now, what do we have here? Oh, come on. It's the usual system that we studied also during the last lecture. It's a layer over half space. Why? Because if we don't go at a global scale, we should deal with flat models. And as we discovered for body wave tomography during the last lecture, the most realistic model is a low velocity layer over a half space. And we did it. Direct, reflected, refracted, travel times. Is it okay? It's exactly the same. But now we are thinking, and actually you have been asking, what are all those waves bouncing up and down? I told you, those are multiple reflections. So wait a second. Maybe here there is the same condition of a plate. Is it possible to build interference between multiply reflected waves? Now you have 1 minute to answer, and I want the right answer. The answer is yes, because otherwise we can go now. But what is deciding the amount of reflections that can interfere? For the plate, oh well, that was perfect. All the energy is trapped here in the plate. Free, free, rigid, rigid, whatever, all the energy is trapped there. In a low velocity layer over half space, who is deciding how much energy will be trapped there? The impedance contrast. Because actually, the ray can arrive here, part of the energy will be reflected, part of the energy will be transmitted, right?
Right.
Good. How much? Well, it depends on the impedance contrast. And if the impedance is strong enough, less and less energy will be lost in the half space. And in any case, if this velocity is lower than this one, there will be a critical angle there, beyond which we have critical reflection. And all the energy will stay there. How much and when, it will be decided by the impedance contrast. So it's like a plate if you want, but it's more complicated because we have to admit that part of the energy can be lost. All the energy that is arriving here with an angle less the critical angle will go down, it's lost forever. Goodbye. But part of it can stay here and interfere. So actually, if you want, love waves are like VSH waves interfering in the plate, but in a layer over the half space. Question before going on with the algebra. What if the velocity of a layer is larger than the half space? Then we can go. Because actually, no critical angles. And every bounce will lose energy there, and sooner or later, all the energy will be in the half space. No interference. Because for Snell's law, the angle is larger. Right?
Yes.
No critical angle. So energy cannot be trapped there. Low velocity layer can trap, as waves know. So if you want, it's like a waveguide, but it's not perfect. We have a free surface, but there we have an interface of discontinuity. And this is what we have to develop. So a little bit more algebra, but we're going to gain some more, how to say, control over it. Now this is the last, and we have to squeeze it in half an hour. Because on Monday, I want to discuss free modes of the Earth. You can relax. Free modes of the Earth in a more complicated geometry are nothing else than love waves and Rayleigh waves interfering on a circle. So, just since today, P waves, S waves, PSV, SH, PSV, Rayleigh, SH, love, Rayleigh, spheroidal, SH, love, torsion. End of the story. Just as a scheme. Okay? Now, what should we do now? We have to do what we have done before, but taking into account that in the half space we can have energy. So what we have to write here is the equation, the trial solution for displacement, uy1, and in the half space, uy2. You can do the same dealing with the geometrical condition, but in my opinion, it's easier to proceed as we did before. Now look, ray going up, ray going down, ray going down. A, B, C. Omega t, omega t, omega t. Kx has to be common to all of them. Horizontal apparent velocity, ray parameter, it's the same. Whatever is happening downstairs, ray parameter is always the same, if you remember. Surface waves are dealing with the same stuff, but ray parameter is containing what we're going to call phase velocity. So we're looking here for a solution, K, that is omega over C, eigenvalues, common to all of this, to all of these three components, and dealing with what? Okay, horizontal propagation, Z that is taking care about what's happening downstairs, C and B are beta, in the layer and in the half space. But, look here. We have to deal with something that is damped in the half space. Otherwise, there is no possibility for the energy to stay in the layer. That's why here I'm writing just this, not this. What does it mean? That R beta 2, it's written also in the next one, this has to be always less than this. That's a necessary condition for interference. If it is not, energy will go down. And we cannot interfere. If you want that condition, is related to the fact that the first layer has to have a velocity less than the half space. Otherwise, at any bouncing, energy will radiate. Part will be reflected, but part will be going with an angle. We want this angle to be 90 and energy traveling on the interface. We want critical reflection. Otherwise, no interference. It's going to be lost. It's called leaking. So just in a few meters, kilometers, no energy anymore here. It will be here. So we want to deal with this situation. Can we do that? As you know, once we decide the trial solutions, we have to apply the boundary conditions. Which are the boundary conditions? Free surface. Good. Sigma zy at z equals 0 has to be 0. Just one component. It's SH. I'm lazy. It's Friday. What about the layer and the half space? Continuity of displacement and continuity of stress. So, actually, we have to deal with this. It's algebra, nothing more. Free surface, continuity of stress, continuity of displacement, no radiation in the half space. If radiation, lost. No interference. Look, the last one was not important for the plate, because the plate downstairs had a free surface. So all the energy was trapped automatically. Here, it depends. So, 1, 2, and 3. And that's the condition for staying in the half space. Now, do you think that there are solutions? Yes, otherwise we can go. And the solutions have been found by Edward, if I remember correctly, Sir Edward Love in 1911 on paper, later in the seismographs. And the solutions are this. Oh my gosh. Now that's terrible, because for the first time we have a tangent. Am I right? The first time? No, in the plate there was a tangent. Right? Okay, good. But wait a second. What do we have here? Which are the parameters of a system? H, thickness of a layer. Now it's not 2H, because for plates, since they are symmetric, usually it's H and H. Here H is the total thickness. Okay? Okay, beta 1 and beta 2. Beta 1, beta 2. It's given. Mu 1, mu 2. It's given. What are the unknowns? C. As a function of omega. It's a dispersion relation. Velocity and frequency. But we have a problem here. We have a tangent. So it has infinite solutions. Modes. And it's not linear. For lazy people, the game is over because we cannot solve it. For not so lazy people, we can use plots and look for the solutions. For not so lazy people, we can create a code and find the solutions numerically. For not so lazy people, we are going to follow the first with plots. And what we're going to solve it. But first, let me try to focus your attention on two things. That is something very naive. Let's imagine that the half space is rigid. I'm going to play with this equation here, tuning to its maximum. Let's imagine that this one is rigid. So beta 2 is like infinite. The impedance control is so strong here that all the energy has to come up. But it will be free and rigid. Now, to be rigid, if you write it in a sort of different way, mu2 has to be infinite. Can the tangent be infinite? Right, pi over 2 multiples. Pi over 2. It's like the string with one fixed and one open. And if you remember, there was a 4 instead of a 2. You have to remember this. Okay, here it is the same. Now let's play another game. Let's imagine now that the half space is empty. Mu2 is going to 0. Can the tangent be 0? Yes. Now the argument has to be n pi. And we're going back to the plate. So now you see that according to the ratio between mu2 and mu1, we're going to change from free to rigid and in the middle. But please do remember that there is a range of mu2s that if beta 2 is less than beta 1, this is not working because it will be damped, because all the energy will go in the aspect sooner or later. So in the two extreme cases, we did something similar to the string with open and closed end. But in reality, like Russ and the mentor, mu2 is larger than mu1, so we have to work it out. Now there are many ways to solve this equation here. This is one way to plot the left term and the right term in terms of omegas, c's, and stuff like that. I created an animation that maybe is going to show to you something better. By the way, let me tell you one thing. The solutions of that problem, the c's in the omega k plane or the c's in the omega plane, this, and I'm going to plot them, these are called eigenvalues. Once you get the c's, you go back and you write the u's, uy1, uy2. Those are called eigenfunctions. And these are called log waves. Okay, this is not an animated version. Now, let's take this. You can plot this. You see, this is not containing frequency. This is. Okay? So this is a sort of a standing curve in this plot here. Beta 1, beta 2, and this is the tangent of the left and changing with omega. It's not animated. I'm going to show it to you one. And this is the version of your textbook. Now, this is the most important picture for today. What do we have here? Let's look the bottom right cartoon. We do have here as a variable this psi here that is here. Look, omega h, this is r beta 1 actually. Oh, by the way, sorry. If you collect this, if you collect C, here you will have K, and this will be r beta 1. So it's like the plate, if you want. But that's the standard way to write it. Okay, so that's the Greek letter. Now, this dashed curve is the right hand. And we're looking for intersections between curves. Now, what about the tangent? The tangent is periodic. No way out. It will have branches. Okay. Now, this is the solution for a specific model. It's the model that we have considered when we have dealt with body waves during the last lecture, last -1 lecture, it was the same day, and we were looking for reflection coefficients and transmission coefficients. It's crossed over the mantle. So, 3.9, 4.6, and you see here the values. The dashed curve is the right curve. This is the branch of a tangent that, increasing frequency, is going to do something like that. I've created an animation, I hope it's going to work. It was a grapher. Let's see. Oh my God. Each time I have to replot it. View. I hope this is going to help you. I'm not sure. And I want to do the animation. Wait. Okay. Here we are. Now, stop there. Not there. Oh my God. Good. What I was writing here was the right term and the left term exactly as in that plot. Intersections are the solutions that we're looking for. Now let's start from 30 maybe. Okay, good. And now let's give a look to this. 30 seconds. At 30 seconds, the tangent term of this equation is this. You see that there is a point, there is a crossing point. That's a solution. Now, 30 seconds and look at the, okay, well, it's in the next plot. It's labeled n equals 0. It's going to be called fundamental mode. Now let's give a look to 10 seconds. Now the first branch has been rising. The intersection now is running in this way. Look, I'm decreasing the period, and intersection is going to lower values of velocity. You see? So let's try to follow it. omega velocity, beta 2, beta 1. This mode here is starting with beta 2 velocity. When it's decreasing, 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 it's going asymptotically to beta 1. But sooner or later, a new branch will enter. Here it comes. I hope. Okay, look. That's the second branch of a tangent. Now it's entering. And then it's going down. Then a third one. Where is it? A fourth one. And all together, they will try, now we have to enlarge. Okay, look. They will try to go towards the limit. So what I'm saying is that you have an infinite number of modes here, starting with beta 2, then going to beta 1. What's going to happen there? Let's give a look to the eigenfunctions. Okay, this argument is too important to be solved within 10 minutes, so Monday we will go back to this. But please grab it as much as possible. Now, let's imagine that we have solved the problem of C's. Now let's give a look to the displacement. 30 seconds. 30 seconds. Now, 30 seconds time phase velocity is wave. Please notice that it is 130 kilometers. It's huge. Long period, large wavelengths, because we have large velocities. We have just one solution there. And the solution is part of a motion in the layer, part of a motion in the out space, but it is depth. This is a mixture of cosine and sines. Then, let's go to 10 seconds. Look at this. This is becoming trapped into the layer. And actually now it's here. But at 10 seconds, a new branch was entering, the first higher mode, and with a higher velocity. This velocity is higher than this one. What does it mean? Well, 45, 39, and it's deeper in the Hall space. Then 3 modes are in. 1, 2, and 3. And here you are. They all share the feature that in the Hall space they are depth. In the layer, they can have 0 nodes, 1 node, 2 nodes, and so on. It's like a plate, but part of the radiation is in the Hall space. How much? Well, it depends on the values. Again, if you take the Hall space as free vacuum, nothing is there, and we're going back to the plate. If it is rigid, well, it's like a plate, but here displacement has to be 0. If it is not rigid, but its velocity is larger than the layer, most of the energy will stay in the top and can interfere with these modes. Now, in the Earth, crust over mantle, sediments over bedrock, they all share this feature here. At a global scale, we have core mantle boundary and the free surface. That's why I was putting this picture here. No, this is too much for today. I want to show you this, because I want you to remember. P waves, long time ago. S waves, long time ago. Radio waves, not so long time ago. with a free surface. You know what? In a layer over the L space, P and SB waves are Rayleigh waves. But what should we do? Not for me, I'm too lazy. What should we write here? Ux and Uz, up and down. In the half space, Ux and Uz, damped. Two components of stress, two components of displacement and stress at the bottom. It's too much. It can be shown, but we will not do, that Rayleigh waves and love waves share a very similar feature. And my main message to you is that Rayleigh waves in a layered structure are dispersed. Not in the half space. Please remember this. In a half space, love waves do not exist. They cannot interfere. There is nothing there with which they can be reflected and interfere. If we put a low velocity layer over the half space, love waves exist. They are dispersed. Rayleigh waves that were still there are there and dispersed. So the key concept for surface waves is dispersion. Now let me ask you, and that's why this is the solution plotted following your textbook of the solutions. It's called love wave dispersion. These are the periods that same session we're considering, 30, 10, and here it's 5. They correspond to this animation here if you want. 30. You see just one solution. 10. Oops. Well, okay, it's there. And then 5. 3 solutions. If you increase, you will have infinite. I cannot increase if you go to shorter periods. Now, since I think that for today it's too much, let me ask you one final thing. Okay. Look at this plot that I love. It's like this, what I was trying to do that. Do you think that it is in some way resembling the plate one? Trust me, if we answer this question in 2 minutes, for today the game is over. How can you compare this plot here with no, I skipped that one, don't worry. This one. This. It's phase velocity, c, versus frequency in both cases. What's happening there? We have the same concept, modes, accommodating zeros along depth, but we have a difference. There were infinites. Where have they gone? Why we truncated them? Give me this answer and I will be happy for the weekend. It's simple. Let's think what we did before. Infinite phase velocity was something that was bouncing up and back with normal. If in the layer over the L space we bounce up, down and up, we are before the critical angle. So every time energy will be radiated here. After some bouncings, all the energy will leave. they cannot exist. So the ray to interfere, let's imagine that we have IC here. It has to be larger than. Only if it is larger, this will happen. Actually, why we truncated them? Because this cutoff frequency is referring to angles that are beyond the critical ones. In the plate, we do not need it, because all the energy is staying there. If we're moving with angles less than the critical angle, okay, we can do some bouncings, but sooner or later, all the energy will go down. Because remember, every time that we have a ray that is moving like that, energy will. Do you remember the applet about Huygens principle that I've asked you to play with? Only when this velocity is larger than beta 1, we can have a critical angle. And only when we are beyond the critical angle, then we will have critical reflection. Otherwise, energy will go like that. And we cannot have interference. So this cutoff here, in the plate, it was going to infinite phase velocity. Here we cannot. Because beta 2 will be, yes, larger than beta 1, but critical angle has to be overcome. That's why, actually, let me conclude with this thinking for your weekend. Actually, the two differential operator problems that we considered, the plate and the layer over the L space, they are very similar. But their spectrum, in terms of eigenvalues and of eigenfunctions, is different. Have you ever studied the hydrogen atom? Have you ever heard about a continuous and discrete spectrum of something? If yes, well, the layer over the L space case, this is the discrete, and this is the integral part. We cannot see it. It's damped in X. You can do that, but sooner or later it will cease. So if you want in the plate, all the spectrum is discrete. Here, part of it is an integral version, but we're losing because we're looking for something that is propagating along X. So if you want, it's a continuous spectrum. Now, I was hoping to conclude this part, this set of slides. One thing is missing here. The concept of dispersion and how to measure it, and how it can be used. Now, a practical question to you. On Monday, do you have other lectures? I hope yes. When? Because I want to grab from you half an hour. That is our delay. What about your next on Monday?
The next business class will start.
At which hour? The answer will be, it's very, this has to be secret.